Concrete. It's everywhere. It's the foundation of our entire modern world, you know? It's the most used material on the planet, right after water. And it seems so simple, right? Solid, predictable. But what if I told you that inside every single block, there are hidden secrets, a whole chemical story just waiting to be told? Today, we're going to crack its code. Okay, so let's get into it. When you mix cement with water, a whole cocktail of new minerals and hydrates starts to form. Now, here's the problem. Many of the most important ones, like the binding gel that actually gives concrete its strength, are amorphous. That's just a fancy way of saying they don't have a regular, crystalline structure. And that makes them basically invisible to standard analysis methods like X-ray diffraction. So, how in the world do you see the unseeable?
Well, you need a different kind of tool, a high-tech forensic instrument that can interrogate a material on a molecular level. So let's meet our detective's secret weapon.
It's called thermogravimetric analysis, or just TGA. Now, the name sounds super complex, but the idea behind it is actually brilliant in its simplicity. You heat something up, and you weigh it very, very precisely as it burns. It's literally like a forensics lab for materials, revealing what's inside by seeing what comes off, and, crucially, when.
The process itself is pretty straightforward. You take a tiny powdered sample of our concrete and you put it into this special furnace. Then we turn up the heat at a really steady pace, maybe 20 degrees Celsius per minute, all the way up to 1,000 degrees. The whole time, an incredibly sensitive scale is tracking every single microgram of weight the sample loses along the way. And this is what you get. This graph is called a DTG curve, and what it shows is the speed of the weight loss. Think of it this way. A really sharp peak means a lot of weight is being lost very, very quickly at one specific temperature. So for a pure substance like Portlandite, which is a key ingredient in hydrated cement, we see the super clear peak right around 460 degrees Celsius. That's the exact moment it decides to release its water molecules. It's our first clue. That single peak, that one little clue, is the key to everything. Because it turns out we can use these clues to create a unique thermal fingerprint for every single ingredient inside our concrete.
So, the crucial point is this. Every mineral and hydrate, it reacts to heat in its own unique, totally predictable way. When it loses water or maybe carbon dioxide, it does so at a characteristic temperature. This gives each and every substance its own unique thermal signature, its fingerprint. And this just illustrates the concept perfectly. I mean, just look at the difference. Portlandite gives us that sharp signal around 460 degrees. But another common component, calcite, you might know it as calcium carbonate, it doesn't break down and release its CO2 until much, much higher temperatures, somewhere between 600 and 800 degrees. Two totally different suspects, two totally different fingerprints. See? But, of course, here's the catch. In a real complex cement sample, you don't get one clean signal. Oh no, you get a dozen signals all happening at once. The fingerprints of all the different minerals and hydrates, they all overlap, creating this messy, complicated graph. It's a jumble of clues, and our job as the detective is to untangle them. Now, to solve this puzzle, our detective cannot be sloppy. The interrogation has to be absolutely perfect. Every single detail of the procedure matters if we want to get a clear confession from our material. And just like in a real criminal investigation, the reliability of your evidence is everything. TGA results are incredibly sensitive to the procedure you use. If you change the method, even a little bit, you change the result. Consistency is absolutely the name of the game here. Take a look at this. It's a perfect example. All four of these curves are the exact same material, gypsum. The only thing that changed was the sample size, from just 0.5 milligram up to 10. See, with more sample, more water vapor gets released, and that builds up pressure inside the chamber, making it harder for the rest of the water to escape. And the result? The peak temperature actually shifts higher. It's the same substance, but it gives you a different clue if you're not careful. And it's not just the sample size. The heating rate, the type of gas you have flowing through the furnace, how the sample was dried and ground, even how long it sat on the lab bench. Every single one of these factors can alter the evidence. Our detective has to control every single variable. So once we have our messy graph, how do we pull out the amount of just one substance, like our friend Portlandite? Well, there are two main interrogation techniques. The stepwise method is the simple one. You just measure the total weight lost between the start and end of that Portlandite peak. But the tangential method is smarter.
It actually accounts for the background weight loss from other materials that are also decomposing in that same temperature range. And this right here is why that distinction matters so much. So look at this test. It was done on a sample with a known amount of Portlandite, exactly 23%. The simple stepwise method, because it includes all that background noise, gets it wrong. It calculates 29%. But the more careful tangential method, it draws a baseline, isolates the true signal, and boom, it gets it perfect, exactly 23%. That's the difference between a rough guess and a precise measurement.
So, after all this investigation, what have we learned? What's the takeaway? Well, it all comes down to a few golden rules for any aspiring materials detective. Okay, rule number 1, prepare your evidence meticulously. Number 2, be consistent. You have to stick to the exact same procedure for every test if you want your results to be comparable. Third, use the right technique for the analysis. We just saw that the tangential method is way more accurate for pulling a clean signal out of a noisy background. And finally, number 4, document everything, so another detective can follow your steps and get the exact same result. That, my friends, is the heart of good science. You know, TGA is so much more than just a tool for analyzing concrete. It's a way of seeing the invisible, of decoding the chemical secrets locked inside all the materials that are all around us. And it really makes you wonder, doesn't it? What other mysteries are out there, just waiting to be solved, if we just find the right way to look?